celebrating Srinivas Ramanujan's 134th birth anniversary. The great mathematician, born in 22 December 1887, and he has worked lot of in pure mathematics. Although he did not hold any formal degree or formal knowledge of the pure mathematics, but he contributed extraordinary in the pure mathematics. Ramanujan uh, was a fellow in the university also, and to celebrate his contribution in mathematics, I invite Dr. Trilok Mathur from BITS Pilani. We welcome you, sir. Sir, sir, can you hear me?
Yes, Dr. Priya Mathur, I can hear you.
Sir, good morning and welcome to our session.
Thank you, ma'am. Thank you.
So I want to introduce my student that Dr. Trilok Mathur is an associate professor in BITS Pilani. He has done his graduation, post-graduation, MPhil and PhD from the Rajasthan University, Jaipur. He has a lot of work in the number theory, and he has published 26 research papers in many fields, and he has taken expert lecture in various universities in various conferences. Thank you for accepting our invitation, sir.
Thank you, ma'am. Thank you.
Sir, I would like to invite you and please share your screen and start the session.
Is my screen right now visible?
Yes, sir.
So I'm now sharing my slides.
Yes, sir.
Are the slides visible?
Yes, sir.
Okay. Good morning, everyone. I am Dr. Trilok Mathur. As Dr. Priya has already introduced to me, so working in BITS Pilani since last 13 years in the Department of Mathematics. Prior to joining to BITS Pilani, I have worked 3 years in Banasthali University, and why I'm here is because the Poornima College or Poornima group of institutions, we can say right now, is you can say the first milestone in my journey. When I have started my career as a lecturer, so the first college which I have joined is Poornima College of Engineering. At that time, it is only one college, which is the oldest building of Poornima College right now. So since then, I have a association with the Poornima College. Dr. Shashikant Singh, he's I know very well him. And though I have only worked here in this college for 4 to 5 months, but that association, and because you all of us know that the first love is always in our mind. So similarly, the first place where I have worked, because I'm not saying I'm working, as usually I'm saying that this is the place, you can say this is the temple of education, and we are the priest here. So the place where I have started my you can say praise or my teaching is this place. So I have you can say soft corner always, and I have always wish to come back to Poornima College whenever there is an invitation from Poornima College. So it's very difficult for me to say no whenever there is an invitation from Poornima Institute of Engineering and Technology. Dr. Priya has invited me. And secondly, I'm here because Ramanujan is my hero from my childhood. I clearly remember that in the schools, when we have a book of stories of some great peoples, so there is a story about Ramanujan also in our Hindi book, if I remember correctly. So in that book, I have studied about Ramanujan, and when I have studied about him, at that only by reading his story, he become my hero, and I just want to become like him. But later on, I realized that the genius are not becoming or by only by liking, or they are not made. Genius are genius, and once in a centuries they have born. So everybody is not Ramanujan, or nobody can become like Ramanujan, because whatever he has achieved in his age of 32 is remarkable, or you can say everybody, those who knows the work of Ramanujan can say that that work is very, very impossible for anybody to carry out in his lifespan of 100 years. Whatever he has done is in the year of only 32. And as Dr. Priya has already inform you that he does not have any formal degree in mathematics, but he whatever he has achieved is very, because I think that on the work of Ramanujan right now thousands or hundreds of PhDs has already been produced after the lost notebooks have been find out. So that's why I'm because of these two reasons, that my linkage with the Poornima institutions and because of the love of Ramanujan. So today we are celebrating his birth anniversary. So on these two reasons, I have accepted this invitation of taking a lecture. So today I am going to discuss with you a talk on, initially we have decided a talk on Riemann zeta function. But later on, when I have prepared this topic, and as Dr. Priya also have informed me that the audience or the students are basically the engineering students, and they have not much interest in pure mathematical concepts. So I have converted my topic a little bit, and now I am discussing a very popular problem, or you can say sometimes it is on internet. Some statements are being floated by peoples, but the mathematics people already know that these statements are not correct. But some false statement, by making some false statement, they have gained some popularities, and it will become a popular stunt. For example, after 1 or 2 years, or sometimes in a span of 4 or 5 years, somebody will claim that I have calculated the value of pi and it is not a rational number. But in mathematics, we know that whenever something has been proved, then it is proved forever. So some claims like this, that they have computed the value of pi and it is not a rational number, and some other claims are there that this is so and this is so, to gain some, you can say, popularity. And this is what a attempt has already been made regarding some work on the Ramanujan also. So that part is also related with Riemann zeta function. So I have basically, now my talk is focused on the sum of natural numbers. Okay, and the Ramanujan also has worked on that area. So this is the right day to discuss that particular problem, which Ramanujan has been interested in that, and he also has contributed to this problem. Another so this topic. So this is my overview of the talk. That first I will discuss about the Ramanujan. I already discussed this. Now, why this topic I have selected, that I will explain you. Then we'll discuss the Ramanujan and his proof for some natural numbers. Uh, what we mean by analytic continuation, and how analytic continuation is related to the Riemann zeta function. So these are some points which I would like to discuss in today's talk. So about Ramanujan, this slide is one slide where we can only give the some brief introduction about Ramanujan. You can see this picture at many places of whenever you will see the any statement regarding the Ramanujan. So full name is Srinivas Iyengar Ramanujan, born on 22nd December 1887. And the place of his birth is Erode and Madras. It is earlier in that days it is called Madras Presidency in the Britishers' time. Right now, this place is in the Tamil Nadu district. And he died is in on the date of 26th April 1920 in the age of 32. Father is K. Srinivas Iyengar, and his father is a clerk in a sari shop, and his financial, you can say, circumstances in his family is not so well. So he's means hardly it is a low middle class family, you can say, in which the Ramanujan has been born and brought up. Mother is Komala Tamla, wife is Janki Ammal, and he basically influences with the work of G.H. Hardy, or you can say that G.H. Hardy is the British professor in the Cambridge University, where he read some of the you can say papers written by the Ramanujan at that era, and he has basically the person who identified the talent or the potential in this particular Indian fellow, who is Ramanujan. And he is so much surprised with his brilliance, and he has invited him to Cambridge University, and then it will become a history that whatever contribution he has made in a very low span of time, whatever he has spent in the Cambridge. So that will become history now also. And the Ramanujan also known as the man who knew infinity, because of his some intuitive you can say statement he has made at some different point of time. And the similar name, you also know that there is a movie about the life of Ramanujan, and there is a book also with the same name, The Man Who Knew Infinity. So you can also read these books, and you can see this movie also, that man, The Man Who Knew Infinity, where the life story of Ramanujan has been played. So his area of interest is number theory, infinite series, and elliptical integral. So basically, he has contributed much more in the number theory area. And Dr. Priya has said one thing, but I just want to clarify that I am not a person in number theory. I am working in the area of fractional calculus, which is quietly closely related to the analytical part. I am not a number theoretist, but I have little interest in number theory, but I am not researcher in number theory. So why this topic? As I already tell you that in 2014, a famous YouTube educational channel, Number Pile, this is a channel which is a YouTube channel. In that, two physics professors from the University of Nottingham have proved by simple mathematical concepts that the sum of infinite natural numbers or natural numbers is equal to -1/12. And you can see that we all know that this is not true. I think that those who know the school level mathematics, they know that this sum is not true, but it is equal to -1/12. They have proved by some, you can say, techniques that it is equal to -1/12. So in 2014, it will, you can say at that time, YouTube has been emerged, and people are playing so many tricks so that their video can be visualized by so many people, and it is a tool to get some popularities. And you can see that over 8 million people have been viewed this video till now, and this video becomes so popular in very short span of time. And this particular channel has get so much, you can say, viewership, and you already know that this viewership on the YouTube, what does it mean in terms of money? So this is it, you can say, play that which has been played by this particular YouTube channel. Later on, some mathematical peoples have already been uh, you can say criticized this effort also, and they have clarified that whatever been used to prove in this number pile video is completely wrong. And I will also show you that how it is wrong. But the interest why this topic we are discussing today is because in the lost book of Ramanujan also showed this sum is equal to -1/12 in his letter to Hardy. He has wrote this particular problem, and he has shown that by using his theory or by using his technique, this sum is coming out to be -1/12. But so it means what? That a genius, which I am praising so much, it is my hero, and he did a mistake. No, Ramanujan does not done any mistake. He has just he already aware of that whatever techniques he is using to prove this sum is equal to -1/12 is wrong, and it is clearly stated in his letter to Hardy also. So he know that what he is doing, and he is doing in some other manner, and why it is equal to -1/12, that I will explain you in my lecture. But centuries ago, when the Riemann, he is also a great mathematician, Riemann, Bernard Riemann, because he belongs to a school, German school of mathematics, where the Riemann is the student of Gauss, and Gauss, you know, is known as a prince of mathematics. So Riemann is the student of Gauss, and Riemann has introduced this function, Riemann zeta function, which is the center. Initially, I have thought that I will discuss more about this function. So this Riemann in his function also has proved some formula, and according to that formula also, this sum is coming out to be -1/12. Even Ramanujan has pointed out this in his letter, and because Ramanujan is also interested in Riemann zeta function, and he has obtained some of the values of this function. For example, the values of Riemann zeta function on odd integers. It is entry 21 first in his lost notebook. So he also interested in Riemann problems and the Riemann zeta functions problem. And Riemann zeta function, basically, it is a very, very popular function, and it has gained popular, and it you can say one of the function which is popularized for last 150 years when the problem has been posed by Riemann. So basically, Riemann zeta function is closely related with Riemann hypothesis, which is recently been, I think that 1 or 2 years back, it has been proved, which is Riemann hypothesis, which is known as, and it is a very popular. Uh, uh, it's coming out here. So this Riemann zeta function, you can say, is also a, you can say source where this sum is shown as -1/12. So you can say that another genius did the same mistake. No, this is not the case. Riemann also aware of his work, and he has also not you can say supported this. But because this problem has been popularized so much, so therefore these two names also gained so much popularity in recent years regarding this particular problem. So that's why I have chosen this topic to discuss you. I think that the students are interested in this type of problem because you all know about the series, and I think that it is been known to all of the students, those who have completed +2 course. So what we mean by infinite series and how we'll get the sum of these infinite series. So that's why I have chosen this topic of the discussion. And this problem have become so much popular that a cartoon has been you can say published in 2014 in the New York Times, which is showing that problem, that you can see a magician is there and who is taking the numbers from his head, and it is coming. For example, you can see that it is closely says that khoda pahad or nikli chuya in our Indian proverbs, we can say. So this is what New York Times has also. So that's what you can say is been the gain of number pile, you can say YouTube channel. But this is not a right way of doing it by saying some false statement and gaining a popularity there. So before we'll discuss that how they have obtained this sum is equal to, or why the Ramanujan has obtained his sum is equal to -1/12. I just want to discuss what we mean by the infinite series and all these how we can what we mean by the convergence of the infinite series. So I'm hopeful that all of you know about infinite series, that if we will have some numbers, for example 1 plus, suppose I will add 3, then I will add suppose 10, whatever numbers are there, and if I will adding up to infinity, I am getting some number. Okay, so this is something is called a infinite series. Okay, so we all know about infinite series. Some of the infinite series we all are aware of. One example I have already written here, that this is 1/2, 1/4, 1/8, which you know that infinite GP. So these infinite series plays some important role in the analysis as well as in the number theory also. So that's how the number theory and analysis is related with through the infinite series. So, and they have some interesting results also. You already know one of the popular infinite series, which is Fibonacci series, if you are the student of CS. So I think that you have encountered with this type of series also, series of even numbers, series of odd numbers, in a series of natural numbers, which we are now talking about. So these type of series, if the sum is going up to infinity, then such type of series are called infinite series. Now infinite series are of, basically you can classify them into the two kinds of infinite series. One type of infinite series is what, where the sum has a finite value. For example, this GP, which is 1/2 plus 1/4, it is a infinite GP, and you know the sum of this infinite GP is a upon 1 minus r, where a is half and r is half in this case. So if you apply a upon 1 minus r, it is half divided by 1 minus half. Uh, that's why I want to connect my tab with this, because these all work is very smooth in tablets. So this coming out to be 1. So you can see the sum of a infinite series is a finite number. But if you will add these numbers, and suppose that these number increases in a positive sense, 1 plus 3 plus 10 up to so on, suppose that this is an increasing infinite series, then if you add up them, then the sum is not coming out to be finite. We all know it is going up to infinity as the series will become, the other terms will be going, we are adding them. So then we will say that infinite series can be classified into two kinds. One is convergent infinite series and one is divergent infinite series. So how we define convergent infinite series? So basically, if we will write the sum of an infinite series by S, then convergent infinite series are basically a convergent sequence of the partial sums. So what is a partial sum? Suppose that we have this infinite series as A1 plus A2 plus A3 and so on. If all these terms are there, then we can construct the sequence of partial sums. So first, how we'll define S1 is equal to A1, S2 is equal to A2, A1 plus A2, sorry. S2 is equal to the sum of first two terms. So this is called sum of partial. And similarly, we can obtain S3, which is equal to A1 plus A2 plus A3. So similarly, you can define Sn, which is sum of first n terms of the sequence of this series. So it is A1 plus A2 plus A3. So this is our S3 and so on. So if we will get this sequence of partial sums, and if this sequence of the partial sums, and if suppose n tends to infinity, and if this Sn is finite, if n tends to infinity, this limit exists. So if this Sn when n tends to infinity exists, if this Sn is limit, the n tends to infinity, Sn exists, then we will say that this infinite series is a convergent series. And in that case, this infinite sum of this Sn or this limit is called the sum of this infinite series. So you already know that, for example, we have already done, this is a GP in which we have the sum as 1. And you can also see the sequence of partial sum here. What is the sum of the first term? S1 is equal to half. S2 is what? Sum of these two terms. So S2 is equals to, if you add them, you can see that S2 is equal to 3 by 4. If you'll add first three terms, then you can see that this is S2. If you add these three terms, you will get S3 is equal to 7 by 8 and so on. So you can easily, and now you can easily formulate what is Sn. Sn is nothing but, what is Sn here? Sn is 1 minus 1 by n. And if you take limit n tends to infinity, this Sn is coming out to be 1. So the sum of the series is also coming out to be 1 because the sequence of the partial sum has a limit. Sn has a limit when n tends to infinity. So you can see that this sequence is converging towards 1. Therefore, the sum of this infinite series, half 1 by 4, 1 by 8, 1 by 16 is equal to 1. So this is what we know in mathematics. Now, if you look at this series, which is the series 1 minus 1 plus 1 minus 1 and so on, and suppose we'll call this series, take the sum of the partial sum of this series. So what is S1 here in this case? S1 is 1, S2 is 0, S3 is 1, S4 is 0. So you can see that you will get a alternate sequence of 1 0 1 0 1 0 and so on. And you know that the limit of this series when n tends to infinity does not exist, because limit if it exists, then it should be unique. And you know that when n tends to infinity, if you end up with even number of terms, the limit will become 0. And if you end up with odd number of terms, it will become if you end up with even number of terms, it will become 0. And odd number of terms, if you ending up, it will become 1. And you never knows that infinity is even or a odd number. So this series, when n tends to infinity, is not, you are not sure about that whether the sum is ending at 1 or whether the sum is ending at 0. So we will say that the limit does not exist in this case. So this series is not a convergent series. So you can see this. So therefore, the sum of this series is not defined. Okay. So if the series is not convergent, then the sum is not defined. And if the series is convergent, then the infinite series has a sum, which is the sum, the limit of its partial sum. You can say the sequence of the partial sum. So this is how a convergent series and a divergent series has been defined. So if the series does not have a finite sum, then we will say that the series is a divergent series. So this is one example of the series, which is a divergent series, because here you can see the limit does not exist. Similarly, you can see, look at this series also, 1 minus 2 plus 3 minus 4 plus 5 minus 5. And if you'll check the partial sums here, then you can see that first partial sum is 1, then you will get minus 1. Another partial sum you will get 2, then you will get minus 2. So every time you can see as the n is progresses to infinity, the partial sums are becoming you can say oscillator between plus infinity and minus infinity, because as n is going up to even number of means higher values at even number, the value of the sequence will become negative, and as n is odd, then the value of the sequence, you can say sequence, will become positive, and it is you can say you can see that here also it is very much gaining very high frequency here. In middle it is
Hello.
am I audible? Hello?
Yes, sir. Now you are audible.
अभी तक नहीं आ रहा था आपको आवाज?
नहीं सर, बीच में 2 मिनट्स ऐसा हुआ जब वॉइस ब्रेक हो गया था, बट नाउ इट्स अगेन ऑडिबल.
ओके, अभी ठीक है?
यस सर.
Okay. There are some hands also there. Anything?
First you complete the session, sir, then we can unmute them.
Okay, okay. So, so I am again sharing the slides. So you can see that this particular series, which I have already shown you, this particular series, they have used some tricks so that this particular series has a sum which is a finite sum. So, and Ramanujan also has used some techniques. What Ramanujan has done, that I'm also going to explain you. But first, I'm showing you that how they have got their sum as equal to minus 1 by 12. So what they did, they have first got the sum for this series. So they have said that write as this sum, which is 1 minus 1 plus 1, then minus 1, and plus, and so on. And you can write this series again by as, and you know that in case of series, you can write the series by shifting one term. So they have written it by shifting one term. So it is 1 minus 1 plus 1, then minus 1, and so on, if you will do it like that. So what happen, if you add these two series, these two terms, you can get 2s, and it is equal to 1. And all these terms, if you add this term minus 1 with this, it will become 0, plus 1 with minus 1, it will become 0, minus 1 with plus 1, it will become 0. Similarly, plus 1 with minus 1, it will become 0. So all these terms will become 0. So 2s coming out to be 1, and it will say that this sum is equal to half. So they have shown it very nicely in a nice manner that this sum is coming out to be half. Similarly, they have obtained the sum for this series, which is again, if you write this s and by shifting one term, so you can write this is equal to s, and s is again this, and by shifting one term, 1 minus 2 plus 3 minus 4, and if you add them, so then you will get 2s is equal to, and you will get this sequence, 1 minus 1 plus 1 minus 1, and so on. And you know that sum of this series you have already obtained. This series is equal to half. So you can say that 2s and s is coming out to be 1 by 4. Okay. So they have shown by using some tricks that by shifting the terms, which is according to them is you can say in the case of sequences and series, or to get the sum of the series, we generally do this, and therefore we can say that this sum is coming out to be 1 by 4. And then they have applied this technique here also, and the same manner they have did this. So s is again their sum, 1 plus 2 plus 3 plus 4, and so on. And I'm writing this series as s2. So this is s2, this is s1. So s2 I am writing like this, that it is equal to 1 minus 2 plus 3 minus 4, and so on. And if we'll take the difference, so s minus s2 is coming out to be 1 minus 1 is 0. So it is coming out to be 4 plus 8 plus 12, like this, and so on. And now this is nothing but 4s. And if you simplify this, then you will get 3s is equal to minus s2. If you simplify this equation, you will get 3s is equal to minus s2. So you can easily compute that s is equals to nothing but minus 1 by 3 s2. S2 we have obtained as 1 by 4. So this s is coming out to be minus 1 by 12. So they have shown that in their video, they have shown that in sum of this infinite series is coming out to be minus 1 by 12. So, but when Ramanujan obtained this sum, he wrote his letter to G.H. Hardy in 1913. So he says that I am very much gratified on pursuing your letter of the 8th February 1913. I was expecting a reply from you similar to one which a mathematics professor at London wrote, asking me to study carefully from which infinite series and not fall into the pitfalls of divergent series. I told him that the sum of an infinite number of terms of the series is this under my theory. But if I tell you this, you will at once point out to me the lunatic asylum as my goal. So you can see that in the last line, Ramanujan himself has mentioned that this is quite clear from this last line that he already aware of that under his theory, the sum is coming out to be minus 1 by 12, but this sum is not correct. And you can say that in the general sense, this sum is not coming out to be, is not equal to minus 1 by 12. So, but how Ramanujan has obtained this sum, it is also an interesting story. And you can easily see that in this is the original handwritten, you can say the pages from the Ramanujan's notebook. It is available. You can see the whole notebook is available for in many libraries. It is available, so you can easily see that in his you can say entries, he has mentioned that the value of this infinite series is coming out to be -1/12. So in this reference, he has wrote this letter to the Hardy. So what is the way of why and how Ramanujan have been, what is the, you can say, uh, the techniques which is Ramanujan has been obtained to compute the value of this 1 plus 2 plus 3 is equal to -1/12. So I have already tell you one way of doing it, which is given in the number piles video also, that they have computed this sum, which is half. They have computed this sum S2, which is 1/4, and then they have computed S minus S2, which is coming out to be which is coming out to be 4S, and therefore they have concluded that S is equal to -1/12. But remember that for divergent series, because S1 and S2 are divergent series, for divergent series, Niels Henrik Abel, you know about Abel. Abel is also a very great mathematician. And right now, Abel is very famous because there is a prize in mathematics which is equivalent to the Nobel Prize, and that is known as the Abel Prize. So Abel has said one that divergent series are the invention of the devil, and it is a shame to base on them any demonstration whatsoever. So this statement is also pointing towards the video which is uploaded on the YouTube, that by using them one may draw any conclusion he pleases, and that is why these series have produced so many fallacies and so many paradoxes. So Niels Henrik Abel centuries ago has been already been informed the mathematics fraternity that please do not believe on any proof which is based on the divergent series. And you can see that this series S1 and S2 are divergent series. And using divergent series intelligently or smartly, one can prove whatever he want to prove. So that's why mathematics fraternity will never accept any proof which is based on divergent series, and which is been done in this video. But what Ramanujan has done, it is little bit different. It is not same thing. So we are calling the sum which Ramanujan has obtained as 1 plus 2 plus 3 is equal to -1/12. And we are writing one R here, and we are calling it as the Ramanujan summation. Because you know that in the case of mathematics, summation can also be defined in many methods. So this plus which is being used here is not the usual plus here. This plus has certain properties which I'm not going to discuss here in this lecture, but we can say that this summation is called the Ramanujan summation. So the Ramanujan summation is a technique for assigning a value to a divergent infinite series. Although the Ramanujan summation of a divergent series is not a sum in the traditional sense, it has properties which make it mathematically useful in the study of divergent infinite series, for which conventional summation is undefined. So whatever number Philae or Ramanujan has obtained, or the, you can say, by Riemann zeta function you will obtain the sum is equal to -1/12, is not the summation of the usual sense. It is a summation in the Ramanujan sense. Now you can argue that why the different type of summations are there. So if a CS student is there, then he can easily understand that in usual mathematics 1 plus 1 is 2, but in computer science, you know, in binary numbers 1 plus 1 is not 2, it is equal to 0. But this sum is not your usual sum. Similarly, this 1 is not your usual 1. So that's why there is a difference when you are dealing different types of mathematics in different type of situation. But there, the law of the mathematics, whatever you are using in a particular situation, first you have to settle, or first you have to fix these laws. Under those laws, whatever you are proving, it is okay, but it is not okay for the general case. So in a general, but if you are representing in a general manner, and you are gaining, you can say hiding something there, then it is not correct. If you are clear in your thought, if you are setting up something and you are saying that under my assumptions and under my hypothesis, under the setup which I am setting up here, if this is coming out to be this equal to -1/12, or something else, some you can say other fascinating result you want to show, then it makes sense. But if you are using this particular you can say theory where some assumptions are there, but you are showing it to some people, those who are not aware of these assumptions, and you are just gaining a popularity by showing something false, then it is not correct. So we can say that this is equal to minus 1 by 12, and this summation, we have assigned a particular sum to this particular series, which is a divergent series, and this technique is called the assigning a value to the divergent infinite series. So different type of summations are in the literature. For example, there is a Cesaro summation, there is Ramanujan summation, we can say one of the another type of summation, where the sum of this first and natural number is coming out to be not coming out to be infinite. We can assign a finite value to it. So how Ramanujan has obtained this formula. So this I am showing through the slides, because I will also try to use some pen work here, but it will take a lot of time if I'm using my mouse here. Even I'm not using mouse, I'm only using my fingers to show you something. So it will take a lot of time. So I'm just showing you on the slides. If something is not clear, then I will clear you, make you clear, trying to clear you. So Ramanujan has used this Euler-Maclaurin summation formula. So you all know that we can approximate, or you can say we can define integrals as a sum of the infinite limit of the sum. So this S, which is the summation of the values of the function at m plus 1, m plus 2, and so on. If you take the infinite sum of this series, you can get the value of this integral, and these the difference between this integral and this summation will become arbitrarily small, or you can say you can approximate this integral with the help of this sum. So for a positive integer p and a function fx, which is p times continuously differentiable m comma n, this formula has been obtained by many mathematicians, or Euler-Maclaurin summation formula, where EP is called the error term, and this BK is nothing but a Bernoulli number. Now, what is a Bernoulli number? Bernoulli numbers are defined with the help of this infinite series. So if you'll expand this series, x to the power k upon factorial k bk, so the coefficient or the kth of the x to the power k is called the kth Bernoulli number. And it is well established, and if you are interested, then you can easily see in number theory that only B1 is non-zero. Rest all odd Bernoulli numbers, for example, B3, B5, B7, they all are zero. And similarly, you can obtain the value of B2, B4, and so on. All the even Bernoulli numbers are there. But for odd Bernoulli numbers, only B1 is there. And for rest, other Bernoulli numbers are zero. Odd Bernoulli numbers are zero. So we can write this summation formula, which is written in the previous slide. This is the summation formula. So by using this S minus I, where S is this summation, which I am written in the next slide in a shorter form, and I is this integral. So I can say that S is nothing but I plus this term. So in the next slide, you can see that this summation is nothing but I plus this sum. And because the first Bernoulli number is non-zero and rest all odd Bernoulli numbers are zero, so I can only get the terms for B2, B4, and so on. And therefore I can take this sum from k is equals to floor of p by 2 and b2k and factorial 2k, and we can get the odd derivatives at n minus odd derivative at m with some error terms. So this is the Euler-Maclaurin formula, which has been expanded in this form in the Bernoulli numbers. Now Ramanujan has contributed. He took this limit n tends to infinity, or when this p is going to infinity. Just a second. So just when this p is going to infinity, so Ramanujan has computed this limit and he has obtained a constant c here. So by taking limit p tends to infinity, and you can say that some adjustments are there for this error term and all, Ramanujan has wrote this summation formula in terms of this formula, where he has proposed that this cx is the constant specific to the series and it is its analytic continuation. So he then proposed to write this cx. So Ramanujan has proposed to write this cx as a sum of the divergent series for the case x is equal to 0. So now if I will choose the function fx is equal to x, we will get this sum of the series as 1 plus 2 plus 3 is equal to minus 1 by 2. So this is the way of the Ramanujan by which he has obtained the sum of this series as equal to minus 1 by 2. So I'm just showing it to here. So you can see here that if I will put x is equal to 0 here, this left hand, so he has proposes what? That this Cx is nothing but sigma k is equal to 1 to infinity fk. This is what Ramanujan has proposes. So if I want to know, if I will put fx is equal to x, this fk will become k. So I can say that it is sigma k is equal to 1 to infinity sigma k is equal to C0. And now if it is equal to C0, if we substitute x equal to 0, this term will become 0. Here, this term will also become 0. You will get f0 here. And here you can say fx is equal to x. So only first derivative is non-zero. Rest all derivatives of this term will become 0. So only you required b2 here. So this, you can say that you can compute here that C0 is equal to minus of f of 0 by 2. And you can see that here f of 0 by 2 is also equal to 0. And minus b2 f dash x is 1. So it is 1 minus b2 upon factorial 2, which is 2. And b2 you already have no. So C0 is coming up. This f of 0 is also 0 because your fx is equal to x. So when fx is equal to x, f dash x is equal to 1 and all other derivatives are 0. So only f dash x term will survive here. So that is 1 and k equal to 1 term will survive here. Rest all terms will become 0. So B2 will survive here. Remaining all Bernoulli coefficients will multiply by this. Because of 0 of this term, all the other terms will become 0. So only first term will survive. So C0 is coming out to be minus f of 0 divided by 2, which is 0, and minus B2 by 2. And B2 we have known that it is equal to 1 by 6. So C0 is again in the Ramanujan theory is coming out to be minus 1 by 12. So this is how, because this is proposed by Ramanujan. So Ramanujan has proposed to say that this Cx is nothing but can be obtained from this formula in under his theory. Now, what is the theory and how he has obtained all this theory? That is again a big story. And again, you have to see some work of the Ramanujan. Then only you can be able to see that why Ramanujan has proposed this constant, which is sum of this infinite series k is equal to 1 to infinity fx. So now I will move on from Ramanujan to the Riemann, that where Riemann also has done this work. So before we'll discuss Riemann, I just want to discuss one technique in complex analysis. And this technique is nothing but the extension of a complex analytical function. So suppose I have a complex function f of z, which is defined under certain subset of C. For example, fz, and it is analytic. So suppose fz is, I'm taking for example, I have already taken that it is equals to 1 minus 1 upon 1 minus z. So this is my function 1 upon 1 minus z. And you can see that under certain, you can say values of z, when modulus of z is less than 1, I can write this function as an infinite series. So it is 1 plus z plus z square and so on. So if I will define my function by this formula 1 plus by with the help of an infinite series, then you can see that it will represent an analytic function under this region. F of z is equal to, suppose my this function. It is 1 plus z square. Then I can say that my function, this function 1 plus z square is analytic when modulus of z is less than 1. But when modulus of z is equal to 1, then you can see that this function is not defined when z is equal to 1, because 1 plus 1 plus 1 up to infinity, it will become infinity. So my function is not defined when modulus of z is equal to 1. or z is equal to 1, at z is equal to 1. So, and similarly at z is equal to -1, again I have obtained 1 minus 1 plus 1, and I have already tell you that series is also a divergent series, so that sum also does not exist. So only in this reason we can say that this function f of z has some sense, because when modulus of z will become greater than 1 also, this series will become a infinite series and thus function is not defined. But suppose, and on the boundary of modulus of z equal to 1, this function is also not defined. But if I will choose my function to be 1 upon 1 minus z, then this function also behaves like this function under this assumption modulus of z less than 1. And this function is also defined beyond the boundaries of this reason. This is the reason modulus of z equal to 1. So this is my suppose function fz, and I'm calling this as my gz. So you can see under this condition modulus of z less than 1 means here in this reason fz and gz are same. So my function fz is defined as function gz. Now on this boundary, this function gz is not defined, as well as this function fz is also not defined. But outside this boundary means here, outside this unit circle, modulus of z equal to 1, this function 1 upon 1 minus z is defined, while this function fz, which is 1 plus z square and so on, is not defined. So I can extend the definition of this f of z as this gz, because this gz is defined in a more wider or in a more bigger set, because it is not only defined in the case modulus of z less than 1, it is also defined in the case when modulus of z is greater than 1. Even this function 1 upon 1 minus z, which is gz, is defined everywhere in the complex plane only at zeros, only at 1. So c complement 1, at all these points, this function gz is defined. So we can extend the definition of this function fz by using the definition of gz in this whole complex plane. So you can see initially this function fz, which is 1 plus z square and so on, is only defined for the case modulus of z less than 1. But by using the analytic continuation technique, I can extend the definition of this function fz to the reason c complement 1, only accepting at one point. All other points this function can extend it, but then I have to compromise the definition. I have to write the definition of my fz as 1 upon 1 minus z. So I can define a function capital F of z, which is like this, that it is equal to 1 plus z plus z square and so on, when modulus of z less than 1, and it is equal to 1 upon 1 minus z for all other points, means when c complement 1. For all other cases, it is equals to this. So you can see that this function 1 upon 1 minus z is the analytic continuation of this function 1 plus z square and so on. Because this function is only defined when modulus of z less than 1, while this function is defined everywhere except at z equal to 1. And you can say that you cannot extend this function definition of this function when the definition is modulus at z equal to 1. So we cannot extend the definition of this function analytically for the point z equal to 1. Is it clear? So now we will use this analytic continuation technique. So generally what happens in mathematics, we will define the functions with the help of an infinite series. Now we will try a compact form of this series so that this series will become a convergent series. So if the series is a convergent series, then you can say the definition of the function or the function itself is an analytic function. But if the series is not convergent at a particular point, then we can say that we can extend the definition of the function beyond that point, so that my function will make still an analytic function. Because you can see that this function 1 upon 1 minus z is analytic everywhere, only except at one point, which is z equal to 1. So I can extend the definition of 1 plus z square by using this 1 upon 1 minus z further from the boundaries, because earlier it is only defined here, but here also I will define my function f of z. So I can say that this f of z is analytic continuation of my function small f of z. Or you can say that this gz, which is 1 upon 1 minus z, is the analytic continuation of my function small f of z. So I can extend the domain of the function so that the analyticity is not going to be hampered. If I can do it, then I can say that it is an analytic continuation. So now with this information of analytic continuation, I will move to the Riemann zeta function. So Riemann zeta function is basically studied in analytic number theory, which is a part of mathematics, and it brings together analysis with the number theory. Now, there are many, you can say, zeta functions have been studied in analytical number theory. One is Riemann zeta function, then Hurwitz zeta function, Lurch zeta function. So there are many zeta functions which has been defined, but Riemann zeta function has a special place there. So Riemann zeta function, because it is a closely related with number theory, and why it is closely related with number theory? Because of this Euler product formula, that this Riemann has defined his zeta function, that it can be used to find out the distribution of the prime numbers within the natural numbers. So zeta of a complex number s, when real part of s is greater than 1, can be used by this formula, that it is equals to 1 minus 1 upon p to the power s to the power minus 1, where p is the prime, and it is, this symbol is the product symbol. So for different products p prime, we can get this value of zeta s, and it will show the distribution of prime numbers within the natural numbers. So this is a part of the number theory, but I am not going in detail of that part, that how it is related and what is the distribution of prime numbers with the natural numbers. I am moving towards some other formula. So how the Riemann zeta function has emerged, I think that you all know about this series sigma 1 by n to the power p. And you know that this series is convergent when p is greater than 1. Okay. So we already know, I think that if you have done the course in Fourier series, then you done this problem, that 1 upon 1 plus 1 upon 2 square plus 1 upon 3 square. This sum we have already obtained. This sum is nothing but zeta 2. And this is coming out to be pi square by 6 am. I am not wrong in that. So this is the value of zeta 2. So zeta 2, or you can say this series, later on I will tell you what is zeta 2. So this series, which is 1 plus 1 by 2 square plus 1 by 3 square up to so on, and this sum is pi square by 6. This is known as the Basal problem. And this Basal problem have been solved by Euler. And Euler is known as king of mathematics. And by solving this problem, you can say that it has been stated that by solving this problem, it has been announced by Euler the arrival of the king of mathematics. Because Euler gained the popularity by solving this famous problem at that time, which is known as the Basal problem. And later on, Euler has contributed in every branch of mathematics. So that's why the name king of mathematics is given to Euler. So because of this solution of this problem he has proposed, he has started gaining the popularity which he deserved. And right now he known as the king of mathematics. Now zeta, on the basis of this series, Euler later on defined a function which is called as Euler zeta function. And Euler zeta function is defined for all real x, and it is defined as sigma 1 by n to the power x. And you can easily see that this is when x, this series is a analytic function when x is greater than 1. So 1 upon sigma 1 upon and where n is running from 1 to infinity. So 1 upon n to the power x is known as zeta of x, and this series is defined by Euler. And Euler has proved so many formulas. He has obtained the formula for zeta 2, zeta 4, zeta 6. All this he has done, and many other values of zeta he has obtained. But for odd values of zeta, for example, zeta 3, zeta 5, zeta 7, he has not been able to find out a compact form of the sum. For example, 1 by 2 square, 1 by 3 square, 1 by 7 square, and so on. The sum is pi square by 6. Similarly, there is a finite sum for 1 by 2 to the power 4 plus 1 by 3 to the power 4 plus 1 by 4 to the power 4 plus 1 by 5 to the power 4, and so on. So these formulas have been obtained by Euler himself. But for odd powers, for example, 1 by 2 cube plus 1 by 3 cube plus 1 by 4 cube plus 1 by 5 cube, like, and so on, the formulas are not so easy, and they are not been obtained by the Eulers. So Ramanujan has obtained a formula for zeta function, when I have already mentioned in my initial slide that Ramanujan has obtained the formula for zeta 2n plus 1, odd values of zeta. And earlier, the first time when he has introduced in his notebooks, so zeta function have been appeared when he has obtained the formula for zeta 2n in terms of Bernoulli numbers. So Ramanujan's has arrived this formula, but for even values of zeta function, this is also a unique formula which is not been proved by any mathematician earlier before the Ramanujan. And when he has worked with the, you can say, Hardy, he has proved this formula that the Riemann zeta function in his notebook can be written as this formula in terms of Bernoulli numbers. So while for the even values, so while studying the distribution of prime numbers, so later on, what is the Riemann zeta function? So Riemann has generalizes the Euler zeta function to the complex values. So he says that this zeta s can be defined by sigma 1 upon n to the power s, where s is a complex number and it is n is equal to 1 to infinity, and real part of s must be greater than 1. So you can see that this is our complex plane. This is the line where s, you can say, real part of s is greater than 1. So this is the reason where real part of s is greater than 0 and less than 1. And this is the reason where real part of s is greater than 1. So he has defined and proved that this is an analytic function for all this part. The problem arises, you know, that when s is equal to 1, you know that zeta of 1, if you use this series, is what? It is 1 plus 1 by 2 plus 1 by 3 plus 1 by 5. And we all know that that sum is not a finite sum. We know that it is a divergent series. So this series, 1 plus 1 by 2 plus 1 by 3, this is a divergent series. Okay, so you know that when real part of s is equal to 1 or when s is equal to 1, we cannot have the definition for zeta s. So s is equal to 1, but we want to extend the definition of zeta s so beyond this reason also. So for that, Riemann has proved a formula by using the analytic continuation, and he has proved a particular formula which is known as by using the analytic continuation technique. And this formula is the formula for the zeta function which has been given by Riemann. And you can see here that zeta 1 minus s can be obtained in terms of zeta s. So, and this is Riemann has mentioned in his proof that it is true, or this formula is true for real part of s when it is less than 0. So when real part of s less than 0, for that reason, we can say that this analytic continuation of zeta s will work. Still, you can say here that this s should not be equal to -1, -2, and so on. So for these values of s, the Riemann zeta function has not been defined. But by using this formula, Ramanujan has also wrote this, that if you substitute s is equal to 2 in this formula, then what happen? If you put s is equal to 2 in this formula, then what happen? You will get zeta of -1 is equal to 2 to the power s is equal to, you have written as minus s is equal to 2. So this is 2 to the power -1, pi to the power -2, sine s is equal to 2. So it is sine minus pi by 2. Gamma of 2, you already know what is gamma 2. Gamma of 2 is factorial 1. So it is 1. And zeta of 2, we have already obtained, is pi square by 6. So zeta of 2 is also there. So now zeta of -1, if you put s is equal to 1 here, is coming out to be, if you simplify this, so 1 by 2 pi square, it is 2 to the power minus 1, and pi square. Sine minus pi by 2 is minus 1, and zeta 2 is pi square by 6. So right hand side you will obtain as minus 1 by 12. And what is left hand side? Left hand side is zeta of minus 1, and zeta of minus 1, if you use this series 1 upon n to the power s, then you can see it is nothing but sigma 1 upon n to the power minus 1. And what is this right hand side? Right hand side is nothing but 1 plus 1 upon 2 to the power minus 1, which is nothing but 2, plus 1 upon 3 to the power minus 1, which is nothing but 3, and so on. So this is nothing but 1 plus 2 plus 3 plus so on, which is equal to minus 1 by 12. So in the formula of Riemann, which is the extension of the Riemann zeta function from real part of s greater than 1 to real part of s less than 0, but this formula you cannot use for when s is equal to minus 1, minus 2, and so on, because then you will obtain here zeta of s is equal to minus 1. And gamma of s is also not defined when s is equal to minus 1. So therefore, this formula is only workable when real part of s is less than 0. So you can see that here for the Riemann zeta function, we have two reasons where this function makes sense. One reason is here, when real part of s is greater than 1. One reason is here, when real part of s is less than 0. So this reason, which is the reason when real part of s is greater than 0 and real part of s is less than 1 or less than equal to 1, is called the critical reason for the Riemann zeta function. And the number theorists are very much interested in this particular reason of the Riemann zeta function. But my interest, which I have initially decided to discuss, is with the derivative or the fractional derivative of Riemann zeta function, because my area of interest is fractional calculus. So I have just recently seen the fractional derivative of Riemann zeta function. So I just want to discuss it with you also at that time. But because ma'am has says that that would be a little bit heavier for all of you, so that's why I have chosen this particular topic, so that I can show you that sometimes by you can say some people can mislead us by showing some false result. So before believing any video or anything on the YouTube also, if something is there, please see what is the background of the work also, because you can see 8 million views are there for a video which is only just uploaded to gain a popularity. What this is entry 21.1. I have also mentioned what is the Ramanujan's work. So Ramanujan has computed this zeta 2n plus 1. Here you can see the computed zeta 2n plus 1. So he has obtained a formula for zeta 2n plus 1. And obtaining any formula which involves values of zeta at odd integers is really a very, you can say, remarkable formula in his lost notebook. So Ramanujan has also contributed in this Riemann zeta function, but this fallacy, which is 1 plus 2 plus 3 is equal to minus 1 by 12, is not true in general. It is only true when we are considering the conditions of the Ramanujan summation. And that is also making some sense. You can see that that also has some application. 1 plus 2 plus 3 is equal to 1 by 12. If we are giving these values, then they are also having some sense. And this I am just showing you for your interest. If you are interested, then you can see that there is an application of this formula, which is 1 plus 2 plus 3 up to so on is equal to minus 1 by 12. So these are two, you can say, area of the physics. One is string theory, where you need a 26 dimensional spaces. So in the 26 dimensional space where you want to study in the physics, so in that space, there is the application of the formula which I have already been discussed with you. And similarly, there is also known in the physics as a Casimir effect. So what is Casimir's effect and what is the application of it? It is another topic and which require a lot of details to discuss. So because of the time constraint, I have already taken so much time of you. So I'm not going in detail of these topics. But if you are interested in all this topic, I'm just showing you some references or bibliography which I have used to prepare this presentation. Okay. So I'm hopeful that this topic or this talk has given you some of the view that what is the work of the Ramanujan and Riemann zeta function, how it is closely related. So if you have any doubt and any question, then you can ask.
Thank you, sir. Thank you for this enlightening session. Uh, Anyone want to ask anything? So I want to unmute them. Yes, Pritish. Yes, Akash, you can ask. Sir, I think there is network problem. So we should.
If they can send their question through chat box also.
Yes, sir.
Something is
I will share their question through email or WhatsApp.
okay. That
Yeah.
is, I am happy to answer all the problems.
Yeah. Thank you so much, sir.
So shall I stop my sharing?
Hello.
हाँ हेलो मैम आपको आवाज आ रही है
जी sir.
So I have stopped my sharing now.
Yes, sir. So we should end the meeting, sir.
Yeah, from my side I have done. If any queries are there, then you can ask. Any quick query, if anything very important you want to know. One thing I want to say that I will share all this slide with you so that if anybody is interested, then they can see the videos
Yes, sir.
I have mentioned there. There is a lot of debate is going on at that time for this particular video. Also, people have criticized a lot